Hi, everyone, and welcome to Tech Tuesday. As we wait for everyone to jump on here, I'll give a brief introduction. My name is Abby, and I'll be your host today. I work on the marketing team here at FCT Solder, and for today's webinar, we are excited to be featuring Tony Lentz, a field application engineer with FCT Solder, to share his presentation, Fill the Void, a Summary. Today's webinar will be recorded and will be available to you through a link that you will get in your email tomorrow. There will be time for a Q&A session towards the end. You'll see the Q&A tab at the bottom of your screen, so feel free to throw any questions you have in there. If we don't get to your question today, we will be sure to follow up, or you are always welcome to contact us directly. Now let's jump right in. Tony, you have the floor.
Thank you, Abby. Appreciate the introduction, and thanks everybody for attending this webinar. This is titled Fill the Void, a Summary, which is a compilation of data that's been selected from all of our Fill the Void papers and a couple of other works that we focused on, not voiding necessarily, but things like how does surface finish affect solder paste performance. So I've gathered voiding data from all of that in order to make certain points about voiding and what can contribute to voiding, and more specifically, ways of solving voiding issues if you're having that kind of a problem. So like I just said, there are many factors that influence voiding, and we summarized quite a bit of that data. I'm going to talk a little bit about the differences between different types of solder paste, no cleans, water solubles, and ultra low voiding solder paste. I'll briefly cover different alloys and how they influence voiding. I've got some data on solder powder size, which does impact voiding, which I was really surprised by when we ran that particular study. And then I'll talk a little bit about reflow profile and how that can affect voiding. And I've got some data on vacuum reflow and the great benefit that that can provide when voiding problems are cropping up. And then I have some data on surface finishes and how that might impact voiding in solder joints. And then we also did a study on different via and pad designs where we looked at open vias, completely open to the backside of the circuit board, partially plugged or tented vias that had a small solder mask tent printed over them, and then also fully plugged and cap plated via holes and how those influence voiding. And then in all of these studies, we varied stencil designs. And so we did a lot of stencil design work with QFN thermal pads because the test vehicle for most of our voiding studies are QFN components. And then we also looked at stencil design changes for the perimeter IO pads on QFN designs. And then at the end, we'll have time for questions. So why is voiding important? Why are we still talking about this? Well, because voids can contribute to cracking of solder joints. So over time, especially with thermal cycling, you can get joint fatigue and these types of cracks can appear, especially if the voids concentrate at one of the interfaces of either the board pad or the component lead interface. And then that can create a weak spot where cracks can propagate through the solder joint. Overheating failures are a big concern if voiding is extremely high on thermal pads like this QFN image that I'm showing. And then in some cases, like this X-ray image shows voids in BGA spheres, it can create a signal noise issue and where the component's not electrically functioning like you would like it to. We had a customer who was having an issue with voiding on some monitoring and measuring equipment that they were building, and it was extremely sensitive equipment, and the voids in the solder joints actually created enough noise to where their measuring precision wasn't as good as what they needed it to be. So the bottom line is that voids can lead to long-term reliability issues. That's why it's important. That's why we continue talking about it and looking for ways to solve voiding problems. The other reason is it's very difficult to rework voids. If any of you have tried to do that, usually the method is melt the solder joint, put more solder paste or flux down and resolder the component and just hope that the voiding is lower the second time around, which isn't always the case. And there's lots of other defects that occur, obviously, that you deal with every day that are easier to repair. Voids are just very difficult to repair. And so it's better to try to prevent them up front and reduce the sources or causes of voiding in your process. So what are the industry limits for voiding? I just took a few selected industry limits from certain standards. So from IPC J Standard 001 and IPC A610, there's a voiding limit of 30% max area in BGA spheres. 50% max area in QFN thermal pads, which seems pretty high, but that's what the standard reports. And then in IPC 7093, which talks about bottom terminated components, it just references that less than 30% area is typical for thermal pads for voiding, but it doesn't actually give a standard. It instead refers back to J standard 001 for limits. And then in IPC 7095, which covers BGAs, a couple of the different standards referenced are less than 25% area and less than 50% diameter for class 1 and 2 products. And then that goes down to less than 20% area and less than 45% diameter for class 3 products, which are a more sensitive class of product. Of course, there are other standards within that same BGA spec that talk about different types of inspection, different locations, via and pad designs, and then the rules for voiding change depending on all these variables. The bottom line is the limits are really driven by the OEMs and the end users and the expectation of that device. How long does that device have to last? And do voids interfere with the lifespan or the function of the device? And if they do, then you're going to see lower voiding limits applied. Like I've seen voiding limits applied as low as 10% void area on certain components for medical devices, specifically like implantable medical devices, because you really don't want to have to go back in and do surgery and remove a failing medical device, especially if it's a pacemaker. That cannot fail, obviously. And so that's something that you want to build to the highest level of quality to make sure that if voids are a problem, you want to reduce the voiding down to the minimum possible. Here's a fishbone diagram that shows cause and effect for voiding. There's lots of different causes listed on this diagram. I just want to point out the major categories that I'm going to be talking about today. First of all, I'll talk a little bit about the print dispense process, specifically stencil designs. And then we'll talk about the reflow process. Like I mentioned earlier, I'll cover different reflow profiles and also vacuum reflow and how that affects voiding. And then I'll talk a lot about different kinds of solder pastes, including different flux types and different alloys and how that impacts voiding. So let's move on to the data. So within these data sets that I'm going to show you, we've got 6 different solder pastes. There's 3 water-soluble lead-frees, which are A, B, and E at the top of this table. Solder paste type A is typically low in voiding relative to the other water solubles. Solder paste B is typically high in voiding. And then solder paste E falls in between those two. And then solder paste C, D, and F at the bottom of the table are no clean lead-free solder pastes. C and D are pretty typically low voiding, and solder paste F is specially formulated to be an ultra-low voiding solder paste. So right off the bat, here's 5 of those 6 solder pastes that I mentioned. Solder paste A and B are shown on the left, and this chart is void area on the y-axis versus these different solder pastes. These are all run with SAC 305 Type 3 in a ramp to spike linear profile. So solder paste A and B have a significant difference in voiding behavior. You can tell that A is much lower than B, and B is the highest overall voiding on this chart. Solder paste E is statistically similar to solder paste B, where the mean values there are roughly 40% and 39% respectively of voiding for those 2 solder pastes. And then the 2 no cleans on this chart, C and D, have overall lowest voiding, where you're looking at 2% and 1% void area. But water-soluble solder paste A is close to that. It's at about 6% void area, and there's no significant difference between those 3 solder pastes. So solder paste flux alone can contribute, or I like to say it sets the baseline for voiding behavior. So the flux we know has solvents and other ingredients that turn into gases that are trapped in the solder joint, and the flux also influences the wetting or flow behavior of the solder itself. And so if you have a lot of gas entrapment or improper wetting or flow, both of those properties of fluxes create voiding. Here's some data from low voiding solder pastes. So this is a comparable solder paste that we ran on QFNs, which had roughly 3 to 8% void area. We ran that against an ultra low voiding solder paste that had on the same circuit board about 0.4 to 1.1% void area, so significantly lower. Here's some images of actual customer run circuit boards with these same 2 solder pastes. So you can see quite a bit of voiding on this comparable paste on the perimeter pads and the center thermal pad. And then all they did is they switched and ran an ultra low voiding solder paste in their process, and the voiding was reduced to what you see on the right. What about solder alloys? So this chart is highlighting two different types of solder alloys, but 4 different kinds of solder paste. So this is again void area against 4 different solder pastes. From left to right, we've got a no clean tin lead and a no clean SAC 305, and then a water soluble tin lead and a water soluble SAC 305. And you can see by the box plots and by the connecting letters report at the bottom, these voiding values are significantly different from each other. So the water soluble SAC 305 had the highest overall voiding with a mean of about 28%. And the no clean SAC 305 solder paste had a mean of about 11, which is significantly lower. And then the 2 tin lead solder pastes had the lowest overall voiding of 7% and 4% respectively. So generally speaking, tin lead alloys give lower voiding than lead-free alloys. Here's a comparison of some different lead-free solder alloys. So what we have here is the AT type 3 is an anti-tombstoning mixture. So that's a mixture of SN100C plus SAC 305 alloy. 90% SAC 305, 10% SN100C was mixed together to form the anti-tombstoning mixture. And then we have SAC 305 and then SN100C in both type 3 and type 4. And then a variant of SN100C called SN100CV, which has some bismuth added to it. And if you look at the connecting letters report, the voiding levels are significantly different here. So the SN100C alloys gave the highest overall voiding, and those were significantly higher than both the anti-tombstoning mixture, which was mostly SAC 305, and then also the pure SAC 305 solder paste was the overall lowest voiding. So solder alloy can definitely play a role in voiding behavior. So it's not just the flux. The solder alloys themselves have different surface tensions and different wetting and flow behaviors. And so if a particular solder alloy has a tendency to entrap gases, then it tends to create more voiding. Or if, in this case, we've got SN100C versus SAC 305. SN100C is a eutectic alloy. It melts and freezes at one temperature, which is 227 C. So when that solder mass freezes, it all freezes at one temperature, so at one time. And when it freezes quickly, and whatever gases are there are trapped inside. Whereas with SAC 305, you have a fairly wide pasty range. And with the anti-tombstoning mixture, again, it's a pretty wide pasty range. And so some of the solder stays molten while other portions of that solder joint start to freeze, but it gives more time for gases to escape before it freezes totally solid. Here's a chart showing solder powder size and effects on voiding. So here we have SAC 305 type 3, type 4, and type 5 from left to right. This was all run in a water-soluble solder paste with a typical SAC 305 profile, and this is a QFN 10 component. The voiding levels are all significantly different here. So we've got type 3 with 53% mean void area, which is really high. Type 4 dropped that down to 46% mean void area, and then type 5 was as low as 29% mean void area. So pretty significant drop in void area just based on solder powder size. And that was unexpected, actually. That is not something that we've seen in all of our solder pastes. So for example, here's another chart showing that same comparison between type 3, 4, and 5 solder powders, but with a no clean solder paste run with the same profile. And the voiding levels are all statistically identical here. 32% mean void area for all 3 powder sizes. So with the water soluble solder paste, we saw a reduction in voiding as you go to smaller solder powder size, but with this no clean solder paste, the voiding levels were all equivalent. And so it's something to be aware of, that if you're considering switching solder powder size, you might see an impact on voiding behavior. So what about reflow profile? Reflow profile is often an easy go-to to try to fix voiding problems. And that's usually where I go first, because it's something you can switch in roughly an hour and see if it works. So we tested these 3 different reflow profiles in one of our papers. So the first blue highlighted column is a ramp to spike or linear profile. Then the ramp to spike -HT, which is red highlighted, was a higher temperature version of that same linear ramp profile. So the reflow temperature was bumped up by roughly 10 degrees, and the reflow time above liquidus was bumped up by about 15 seconds. And then on the right, we have the ramp soak spike profile, which includes increased soak time between 150 and 180 C in this case. So we added about 40 to 50 seconds of time in that temperature range. Here's a comparison of a ramp to spike and a ramp to spike high temp profile for solder paste A. And these voiding levels are significantly different. The ramp to spike profile gave 6% mean void area, and the high temp version dropped that down to about 4% mean void area. So for solder paste A, increasing the peak temp and increasing the time above liquidus actually reduced voiding a little bit. For solder paste B, we saw the opposite effect. So again, this is a water-soluble solder paste, different formula. We've got the high temp version of that profile gave 42% mean void area, and the normal linear ramp to peak gave 37% void area, which was significantly lower. So changing the profile will have different effects on different solder pastes. So it's best to contact your solder paste manufacturer in order to make the appropriate change in order to reduce voiding based on the solder paste that you're using. Because in this case, like I said, the increasing the peak temp and stretching out the time above liquidus reduced voiding for one of these solder pastes, but increased it for the other solder paste. Here's 4 different profiles compared, again, for water-soluble solder paste B. We have a ramp to spike profile on the left, and ramp soak spike, excuse me, and then the ramp to spike profile follows that, and then the RTS-2 is the same ramp to spike profile but run twice. So the whole idea there was to try to simulate what happens on the second side of double-sided surface mount reflow. So you print, paste, place components, reflow side 1, and then you flip that board over and process side 2. Well, all the solder joints on side 1 are going through the oven again, and they're reflowing again. And does that impact voiding? So that's what we were testing with that. And then we have the high temperature version of that same profile. So if you look at the connecting letters report here, the only differences between the voiding is for the soak profile gave the highest overall voiding, and the ramp to spike linear profile was the lowest overall voiding, but the other two were in between and not statistically different. Here's a test where we ran vapor phase reflow, and we also used vacuum in that same vapor phase system. So on the left, we've got water-soluble lead-free solder paste, and it was run with vapor phase, and it had about 9% void area. And then we ran it with the linear ramp to spike profile in a convection reflow oven for comparison, and that dropped the voiding down to about 6%. And then we ran one of the vacuum options on that vapor phase system, and the voiding was below 1%. So the lowest overall, of course, was with vacuum. But in that case, comparing between a convection reflow and vapor phase alone, just running vapor phase with that solder paste increased voiding versus the convection reflow. For the second chart here, the water-soluble lead-free in the middle, it's a different water-soluble lead-free formula. The ramp to spike profile in the convection oven gave the highest overall voiding, like 37%. And then the vapor phase system gave moderate voiding at about 23%. And then the 3 different vacuum options were tested. So that's the V3, V2, and V1 that you see listed there. And those gave voiding all below 2% for this solder paste. So in this particular case, running vapor phase rather than convection actually reduced the voiding significantly by about 14% reduction. But then running vacuum, of course, dropped it down to almost nothing, like below 2% void area. And then on the right, we have a no clean lead-free running a vapor phase system. So you can see that the vapor phase in that case gave the highest overall voiding, 14% void area by running that in vapor phase. And then when we ran that with vacuum, it dropped to 1.8%. And then when we ran that in a convection reflow with a regular ramp to spike profile, the voiding was the lowest at about 1.4%. So in that particular case, running that solder paste in convection reflow gave a pretty nice low voiding level. But when we ran that in vapor phase, it increased voiding significantly. And then when we turned the vacuum on, of course, it dropped back down to a nice low level. What about using vacuum to rework voiding? We ran that test with one of our particular solder pastes here, solder paste B, which is producing pretty high voiding. On the left, you can see the solder paste B was run in a convection reflow, linear ramp to peak profile, and the voiding is pretty high. It's like 45%. And then we reran that same circuit board through a vapor phase system with vacuum, and the voiding dropped down to like 8% mean void area. So in some cases, you might be able to use a vacuum system to rework existing voids. Although I have heard of tests by certain equipment manufacturers where they've attempted to do this on customer boards and it doesn't always have an effect. But in this particular case, with our test boards, it had a great effect where vacuum definitely helped to reduce voiding running it a second time. What about surface finish effects on voiding? So here's 3 different surface finishes: ENIG, immersion silver, and OSP on a no clean lead-free solder paste. And we've got 3 different voiding levels. So look at the chart on the left. ENIG and immersion silver gave higher overall voiding than OSP for that solder paste. And then on the right, the water-soluble lead-free solder paste, OSP gave the highest overall voiding, and immersion silver and ENIG gave lower voiding levels. And so surface finish combines with solder paste in order to create different voiding levels. And part of that is due to the wetting behavior or flow over the surface. So if the surface finish and the solder paste together create good wetting or flow behavior, then the solder paste has more of an ability to move and fill in the gaps and push gas bubbles outside of itself. Here's a combination of surface finish and profile testing. So we've got a no clean with a ramp soak spike profile on the left and a no clean with a ramp to spike profile on the right. Again, the same 3 finishes were tested: ENIG, immersion silver, and OSP. So on the left, those 3 finishes gave identical levels of voiding. There's no differences. And on the right, with the ramp to spike profile, ENIG gave the highest voiding and OSP gave significantly lower voiding, which is kind of interesting. So just by switching the profile, we were able to change voiding behavior a little bit. What actually happened between these 2 charts, if you look at the numbers, the ENIG voiding level from the soak profile at 9% went up to about 11% when we ran a ramp to peak profile. So using a soak profile in combination with this solder paste on an ENIG surface finish actually reduced voiding a little bit. So we ran that same test with a water-soluble solder paste. So again, we have water-soluble with a ramp soak spike profile on the left and a water-soluble, the same paste with a ramp to spike linear profile on the right. On the left, with the soak profile, immersion silver gave the highest overall voiding at 21%, and ENIG and OSP were much lower than that at 11 to 12% void area. And then on the right, with a linear profile, OSP gave the highest overall voiding, and ENIG and immersion silver were significantly lower. So the order of the voiding based on surface finish flip-flop on these 2 profiles. So again, in order to mitigate voiding, you have to look at more than just solder paste. It's important to look at profile, surface finish, and the combination of all 3 of those things, because that can play a role in mitigating voiding problems. All right, here's a breakdown of just 6 different surface finishes that were tested in one of our works. So we ran 4 solder pastes in this case. We ran water-soluble and no clean, and we ran a tin lead and a lead-free SAC 305 version of each one of those solder pastes. And so we had 4 different solder pastes combined into all these in this data. And then the same stencil design was used for all of these. And the profiles that were used were appropriate for the alloy. So for the tin lead paste, we ran a tin lead profile. And for the SAC 305 paste, of course, we ran a SAC 305 profile. So you can see, just breaking down by surface finish, there's a difference. So we've got immersion tin giving highest overall voiding, and it's significantly higher than all of the others. And then most of the others are tied with B letters and C letter codes, but immersion silver was significantly lower than all of the others, all other factors being equal. So that's kind of interesting. I didn't expect surface finish to have such a big influence on voiding, but it certainly does. Here's a breakdown of 4 different solder pastes that I just mentioned that we tested, and all 6 surface finishes within each solder paste category. So this is all of the data that I just showed, a combined chart, and this is the breakdown in sort of all of the data shown on one chart. So what you've got, just to highlight a couple of points here, the water-soluble tin lead gave the overall lowest voiding with 5 of the surface finishes. And the water-soluble lead-free gave the overall highest voiding with immersion tin, lead-free hassle, and OSP. The others are all kind of in between and in the middle. Here's some pictures showing what some of the voiding looked like on this test. So at the top, we have immersion tin with a water-soluble tin lead paste, 9% void area, so pretty low voiding. That same immersion tin finish was run with water-soluble lead-free solder paste, and the voiding jumped up to 46% area. Pretty big difference just by changing the solder paste. And then we took that same water-soluble SAC solder paste and ran it on immersion silver, which is the third picture down. That voiding dropped down to 8% void area. And then we ran the water-soluble tin lead paste at the bottom with immersion silver, and that had the lowest overall voiding at 3%. So again, I'm making the point that the combination of surface finish and solder paste impacts voiding behavior. Here's again a breakdown now where we've included profile into the mix. So this is a breakdown of paste, profile, and finish. So on the left, we've got a ramp soak spike profile with a no clean paste. All three surface finishes there gave the same voiding behavior, and that's ENIG, immersion silver, and OSP. And then we ran a ramp soak spike on a water soluble solder paste. Immersion silver gave the highest overall voiding in that case, and it's significantly higher than the other two. And then we ran a linear ramp to peak with the same no clean paste. ENIG gave the highest overall voiding, and it was significantly higher than the OSP voiding in that case. And then we ran a ramp to spike water soluble solder paste, that same water soluble, but with a linear profile. And we've got OSP coming in with the highest voiding. So if you look at the colored blocks at the bottom, the ramp soak spike profile with the no clean paste, all the finishes were tied in terms of voiding behavior. And then each one of the others gave different surface finishes gave the highest overall voiding in each case. Again, I'm just continue to beat this point home. Like one of my friends likes to say, I beat points home with a sledgehammer sometimes. And I do that because I have a thick skull and I need to hammer points into my own head. So, so the point is surface finish, solder paste, and profile all influence voiding behavior, and they all have to work together in order to minimize voiding. All right, let's switch gears and talk about via and pad designs. So we had a board built where we put vias in the thermal pads of QFNs. We had two QFN sizes. We've got a QFN 7 and a QFN 10. And you can barely see, but if you look at the solder paste print right around the perimeter of some of those bricks, there's the via holes. So in this case, we just use a standard window pane. We printed paste right over the via holes. And here's pictures of what the different voiding looked like. Now we had 4 different types of via designs. So in this table, the first column is open vias where they're not filled at all. So the solder paste was printed over the via and allowed to flow down to the backside. And those images clearly show there's very little voiding. And then we also processed solder mask tinted boards where we had a solder mask tint kind of partially covering the vias on the bottom side. Some of them were blocked, some of them you could see daylight through. So as solder mask tinting goes, it's fairly random on whether the holes are plugged or not. Again, voiding was very low in that second column. And then if you look at the complete plug option, the third column over, where those were actually filled with a thermal material and then cap plated, so the pads were flat copper and finished with ENIG, there's a lot of voiding going on. And the voiding seems to want to collect around the plugged via holes. And my theory about that is that all those plugged via holes essentially are thermal pathways where heat's getting wicked away out of the solder joint during reflow. And so those are all little microscopic cool spots during reflow. And so that's going to tend to be where the solder paste reflows last, and therefore there's still gases sitting in there around those vias that are going to have a hard time escaping from that solder joint once it all goes liquid. And then on the right, what we have for comparison is the same test board without any via holes at all. So that's just a flat thermal pad, and you can see what the voiding looks like. And it's kind of interesting to compare the complete plugged voiding with the flat thermal pad voiding. The flat thermal pad voiding is much lower than the complete plug voiding in terms of total area. So in this case, it looks like plug-in vias actually increases voiding. And having open vias or partially tinted vias helps provide possibly gas escape routes so the gases can get out, even though that would be downwards or against gravity the way these boards were processed through the oven. Here's a modified stencil that we used on that same paper. And so look at the prints on the left. What we did is we took and printed solder paste around the vias. So we left a clearance around the vias, and then we broke up the print with a lot of window pane bricks in there. But the same area of coverage was used. I think the area of coverage in both of these cases was 65%, if I remember correctly. So we were careful to optimize the area of coverage and leave it the same. The only difference is we didn't print over the vias. And you can see the open vias with no filling, again, very low voiding. The solder mask tented vias in the middle of this table, very low voiding. The completely plugged vias on the right, relatively high voiding again. So plugging vias, while I think it's probably a good, reliable option, it may create voiding problems. Here's another paper where we looked at 4 different stencil designs on the same circuit board. So we're using QFNs, and these are QFN 10mm bodies. We varied the area of coverage from 80% down to 50%. And then we also did different numbers of bricks in the windows. And we used a low voiding solder paste and a ramp to spike profile on ENIG surface finish. Here's the voiding breakdown. So for 50% area of coverage and 60%, you've got pretty high voiding in the 28 to 30% area range. When we increase the amount of solder paste, or the area that was covered, to 70 and 80%, voiding dropped significantly. It dropped down into the 7 and 6% voiding range. And so that was kind of interesting. It's pretty distinct how much that voiding dropped just based on increasing the amount of solder paste we put on the pad in terms of area. Here's a variation on that same paper where we modified stencil thickness. So we wanted to modify the total volume of solder paste in addition to the area. So on the left, the first chart just shows you the 2 different stencil thicknesses. All other things being equal, the 4 mil stencil thickness gave higher voiding than the 5 mil stencil thickness. So increasing the thickness reduced voiding. Then we did that same variation with the 60% area of coverage. Again, the 4 mil stencil gave higher overall voiding than the 5 mil thick stencil. And then when we ran 70% paste area on those 2 stencil thicknesses, we've got identical voiding. So both of these are about the same voiding level at about 10% void area. So the point is, if you have too little solder paste, that can actually increase voiding. So an easy fix for solving voiding problems might be to either increase area of coverage or increase stencil thickness to give more volume of solder paste there so that it can better wet and fill in all the gaps in the solder joint. Here's another test that we ran to change the input-output pad print on these QFNs. So we ran 3 QFN sizes, a QFN 10, a 7, and a 4. We did not use the QFN 9s, which is the second set of QFNs there. We also varied area of coverage between 70 and 60%, and the input-output toe adder was changed from 0 to 5 to 10 to 20 mils. And I'm going to explain that a little further. So what we have here are the 4 different toe adders. And if you look, you can see the length of the paste print is increasing from the top to the bottom. So from the top, that's 0 toe adder, it's 1-to-1 with the copper pad. And then we added 5 mils, 10 mils, and 20 mils. So we increasingly printed solder paste outside of to the toe of those pads. And then the theory there is that the solder paste will pull back. And when it pulls back, it creates a bump of molten solder that lifts the QFN component. And it lifts the QFN component enough to allow some of the gases to escape from underneath the body of the component at the thermal pad. And so that has an effect of reducing voiding. At least we saw that in a prior study, and we wanted to duplicate that in our work and combine it with our stencil designs for area of coverage and some other things. So here's the data for the QFN4 component. From 0 toe adder up to 20 mils of toe adder. So from left to right, you can see voiding's dropping significantly. It dropped from 16% down to about 11% void area, which is significant. For the QFN 7, the same trend from left to right, voiding's dropping as we add solder paste to the toe of those input-output pads. And then for the QFN 10, we've got the same trends here. So increasing the length of the toe adder will reduce voiding on these QFNs. Here's some pictures that show that. So these are the QFN 7s, plus 5% toe on the left. So you got 23% void area there. And then when we went to plus 10% mils on the toe, that dropped to 15% void area, and then plus 20 mils on the toe to the right, dropped to 5% void area. Now, this is a great solution if you have room to do that. But in real practice with QFN, sometimes those input-output pads are pretty close to other components or via holes, and you might not always be able to print that much paste outside on the toe of the pads. But if you do have room to do that, this might be a good option to reduce voiding on QFNs. And what we saw in our paper, like I said, we varied paste area and stencil thickness. The toe adder by far had the biggest effect on reducing voiding. The paste area and stencil thickness effects were insignificant compared to modifying the toe. All right, so in summary, here's how I'd recommend filling the void. If you're having trouble with voiding, here's some ideas to help combat that. Use lower voiding solder pastes. Like I mentioned earlier, solder paste kind of sets the baseline for voiding, and then all the other things I've been talking about can influence that. So if you've tried all the other things and you don't have any other options, changing solder paste might be helpful. I recommend you choose alloys that reduce voiding potential if you have that option. Just be aware that, and if you're considering a switch in alloy, maybe for cost reasons, be aware that switching alloys might have an impact on voiding. It might go up, it might go down, it might have no effect. It just depends on what's creating the voids on your devices. Solder powder size also may have an effect. So if you're also considering a switch, say from type 3 to type 4 or type 4 to type 5 solder powder, realize that for some solder pastes, that can have an impact on voiding. Voiding may change when you make that switch. I definitely recommend setting the reflow profile for the solder paste that you're using. And it's important not to believe that one change to a profile can reduce voiding for all solder pastes. That's not true. Every solder paste is a little bit different in formulation and how it reacts to profile changes. So it's best to contact your solder paste supplier to get the correct reflow profile change in order to reduce voiding for the work that you're building. And then if you have the option, I recommend using vacuum reflow. That reduces voiding regardless of all these other factors. That's the one thing I highly recommend. If people are considering putting in a new reflow process, a new oven, I would highly consider looking into one with vacuum, because that's going to reduce voiding regardless of all these other factors. Surface finishes may have an effect, like I showed a lot of data on that. Surface finish in combination with solder paste and profile certainly can moderate or change voiding. And so I know a lot of you don't have control over the surface finish that you use, but if you do, just realize that you might be able to pick a surface finish that helps reduce voiding if that's a problem. And then VN pad design certainly influence voiding. And I've seen a lot of other work around this, especially for bottom terminated components. There's some interesting theories on how to put solder mask up on the pads in order to create sort of solder dams around vias so that the solder can't interact with the vias themselves and the vias can't introduce gases or other materials up into the solder joint. But then again, what you'd be looking at is a broken up solder joint on a thermal pad. And that broken up solder joint is going to look a little weird under X-ray, but it might overall still make a more reliable solder joint. That's the whole point. So if it makes a more reliable solder joint, I'm all for it. If you do have via in pad, we recommend printing paste around the via holes. Don't print directly over the via holes. That's just to help maximize the amount of paste that stays up in that solder joint. Otherwise, if you print right over the via holes, solder paste is just going to flow to the back side if those vias are open. And that's going to reduce the amount of solder present, which we know from changing stencil designs definitely can increase voiding. And then designing the stencils with high paste areas and gas escape routes had a big effect, as well as that IO pad toe adder for QFNs. So all those things had an impact on voiding in all of this work. I know that's a lot of information coming at you. I appreciate your patience in listening to this talk. So I thank you for your attention. Thanks for hanging in there with us. And now we have time for questions.
Awesome. Thanks, Tony. Yeah, let's see if we have any questions. All right, we have one question. My experience with open/tented vias has shown more voiding than what you guys are showing. Why do you think that is?
Well, I think in some cases, open via holes will introduce gases up into the solder joint or drain away solder paste from the solder joint, creating a lower volume of solder. And both of those conditions can increase voiding.
Good to know. Thank you. Let's see. Is there a relation between environments and voiding?
Yeah, certainly, especially with solder pastes that are less tolerant to environment and environmental changes. Water solubles are pretty notorious for absorbing moisture from the air, especially in humid environments. And any moisture that absorbs into a water soluble paste is going to turn into a gas during reflow. And that gas is going to potentially increase voiding in the solder joint. And then also with no cleans, they will also absorb moisture, although at a much lower rate than water solubles. And typically that's not a major cause of voiding with no cleans. But then again, if you work in a dry, warm environment, that can evaporate solvents out of the solder paste as it's used, as it's open to the air. And that can potentially contribute to reduced voiding. But at the same time, the longer the solder paste is exposed to air and is at room temperature, it's losing activity. And as it loses activity, voiding behavior is going to be influenced. It's going to change.
Definitely. Thank you. How do you know how long to run the vacuum in a vacuum oven?
I would go based on the vacuum oven manufacturer's recommendations. Typically, I think they're pretty short cycles, like anywhere from 5 to 20 seconds, and they're only pulling a partial vacuum in there. But part of that is also dependent on the production flow. So if you need to get a certain number of boards per minute out of that oven, that might limit how long you can actually pause with boards in that vacuum chamber to pull down vacuum. And in a vapor phase system, the ones that I've worked with aren't conveyorized, although there are conveyorized options. Vapor phase is a little different process where you're loading boards into a chamber and it seals and then it runs through its cycle. And using vacuum in there is relatively simple because it's already a sealed system. And so I think the amount of time for vacuum pull down in there might be shorter than a convection vacuum oven, although every piece of equipment's always, they're always making improvements to those systems to try to speed up production flow. So I'm sure there are pretty comparable options both ways.
Great. How does increasing the toe length work to reduce voiding?
So that is something that's kind of interesting, where we've seen 2 other companies do studies on that, and they had the same results that we did. In fact, we jointly presented that work in one technical session at one of the major industry conferences, and we all had the same theory. There is the solder paste pulls back off the solder mask and forms a liquid solder bubble on the IO pad. And that bubble height is going to vary based on how much you overprint. So the more you overprint off the toe, the more solder is present, so it forms a taller bump. And as the bump height increases, it can actually be much taller than the molten solder that's melting underneath the belly of a QFN. And so that those bumps on the IO pads lift the QFN up off of the solder paste deposit that's underneath the body on the thermal pad, and that allows a gap for gases to escape. So that's our theory on why that works to reduce voiding.
Awesome. Thanks for sharing that.
I've seen a similar theory actually along those lines, where some of our competitors are selling preforms, which I think are great for different uses. And what they did is something similar, where they put a preform in the solder paste print on the thermal pad to sort of act like a kickstand, if you will, lifting the QFN component. And so it basically let that QFN component stay off contact from the solder paste while the solder paste started to reflow. Then the preform melted and the QFN laid down in contact with the solder paste, and that had a dramatic effect at reducing voiding as well. So a different idea on how to approach the same problem, but lifting the QFN seems to help.
Awesome. Thanks for diving into that. So another question, how big were the vias you tested on?
We had 13 mil drilled vias, which were plated down to like 10 to 11 mils in diameter, finished size.
Okay, thank you. What is the acceptable void percentage on an EPAD under a QFN?
Well, general industry guidelines say 50% maximum, but I've seen customer requirements that are lower than that. I think the rule of 25% is commonly used just because that was the first voiding rule that was given in our industry in the BGA standard. And so I hear that number thrown around a lot, but it really depends on the application. I mean, 50% void area seems pretty high, but if it's adequate to conduct heat away from that QFN, then your solder joint's doing the job it was supposed to do. But if it doesn't and it's failing, then obviously you might want to reduce that void area. So it really depends on the application and the expected end use and the lifespan of that device.
Great. Let's see here. Someone asked, we are going to solder CGA components. What kind of solder paste do you recommend? We solder with tin lead and the PCB finish is HASL. So
you've got tin lead solder paste, tin lead hassle, and you're going to run CGAs. I would recommend certainly a low voiding solder paste if you have an option to pick one. I guess it depends on if you're washing that solder paste off. If you're going to wash the flux residue off, I would go with a water soluble tin lead. And if you're going to leave it on, obviously pick a no clean, but pick a low voiding no clean.
Great, thank you. Let's see. A PCB with OSP surface finish that has been exposed to humidity after one reflow cycle is more prone to produce voids on the second reflow. Is that the case?
I have not tested that. That's an interesting theory. That may be the case. Surface finishes, generally speaking, if they oxidize, humidity seems to enhance oxidation as they're sitting open to the air. And also certain surface finishes like OSP could be a little hygroscopic, and OSP itself might absorb a little bit of moisture. And I've seen, it depends on the solder paste actually. OSP can give you really low voiding levels with say like tin lead solder pastes, but with lead free, it seems to increase voiding levels pretty dramatically and give some of the highest that I've seen. And I didn't necessarily test humidity in the environment, and the boards weren't open to the air for very long, but I think anything that builds up an oxide on that surface finish, and the ones that would be susceptible would be OSP, immersion tin, immersion silver. Those things are going to oxidize a little bit as humidity levels go up. And that's going to limit or retard the flow of the solder over that surface, which by its very nature, if you limit the flow, that means you're going to have gaps in the solder joint, which are voids. So controlling humidity levels is important, and minimizing air exposure of the finish itself is also important.
Sounds good. Thank you. Have you experimented with LGAs with a grid of pads underneath the part?
We have not. No, we haven't done any work with that.
All right. We'll give it another minute just to see if anyone else has any questions. This presentation will be available to you tomorrow. You'll get a link in your email. Just to address that one more time. Well, since we're coming up on our time here, we'll start wrapping things up. But thanks again for that great presentation, Tony, and for joining us today.
Certainly. Thank you all for attending. We appreciate that.
Yeah, definitely. Thank you everyone for your attendance and participation. Don't hesitate to reach out to us with any questions, and be on the lookout for future topics. We look forward to seeing you in December for the next Tech Tuesday. Have a great rest of your day, everybody.
Bye, everyone.